Okay, well, thank you very much. I'm sorry for the delay. Um, it's a pleasure. I would rather prefer to be in Rio than where I am. I'm actually on vacation, so this is one of these experiences provided by the pandemic, which is to give a talk in the middle of my vacations. Um, anyway, I want to thank Marta and Renato for the invitation, and um, so the what I want to tell you a little bit about it's these multiplicity-free fibrations and symplectic gerbes. Actually, I'm going to spend most of the time talking about what's called isotropic fibrations. I don't think I will say much about multiplicity-free fibrations apart from the definition, but we'll see. We'll get there, given it's just a half an hour talk. Um, anyway, so just to agree on these conventions, so in this talk, by a fibration, I just mean a submersion with compact connected fibers. And most of the time I'll be working with a fibration. Towards the end, I'll be working with a singular fibration. And by that, I mean that we have a smooth map, and there is an open dense subset where the restriction becomes a fibration in the first sense. Um, so the main or the first definition in this talk is this notion of an isotropic fibration of a symplectic manifold. So this means what? It means I have a fibration, and the fibers are isotropic, as the name suggests. But there is this extra condition that the symplectic orthogonal to the fibers is involutive. So it's again a foliation. These have appeared in the literature with a different name. They are usually called symplectically complete. So there is missing a not verb mode. Symplectically complete isotropic fibrations. They go back to Paulette Lieberman and Dazor and Delzin. I will omit these terms symplectically complete. First of all, because I don't think general isotropic fibrations, where you omit the second condition, you can say much about them. And I will only work with these ones. So for me, these are isotropic fibrations. Now, of course, people are, I'm sure, are familiar with Lagrangian vibrations, where are just a vibration where the fibers are Lagrangian. And in that case, the second condition is automatic, since the symplectic orthogonal to the fibers coincide with the fibers themselves. So these are generalizations of Lagrangian vibrations. And eventually, what I'm interested in is the singular version of isotropic vibrations. Those are the multiplicity-free vibrations in the title. But we'll have to go through first the regular case, so the case of non-singular vibrations, and then we can move to those. Now, I mean, there are a few motivations to look at these objects. Of course, if we remember that Lagrangian vibrations are, in some sense, geometric versions of integrable systems, these isotropic vibrations are more general than Lagrangian vibrations, and in fact, they are, in some sense, geometric versions of what is called non-commutative integrable systems. So I'm not going to tell you precisely what is a non-commutative integrable system, but the idea is that instead of having first integrals or functions in evolution, you have functions that satisfy some commutation relations. So there is some Poisson structure in the background, and these have to satisfy some property. But that's how you can first approach these things. These non-commutative integrable systems appear in mechanics as super integrable systems, and then there are also other names. And so if you want, this is a geometric version, these isotropic vibrations is a geometric version of these non-commutative integrable systems. By the way, if anyone wants to interrupt, please feel free to unmute yourself and ask questions. So the same way you can use Lagrangian vibrations to probe symplectic manifolds, to probe the geometry of symplectic manifolds, probably you can use these isotropic vibrations to do that too, and get a bit more freedom. But this, as far as I know, has never been tried. My main motivation actually comes from Poisson geometry. These isotropic vibrations provide what may be called minimal symplectic realizations of Poisson manifolds. But I'm not going to go into that today. So the very first thing that one should try, given what we know about Lagrangian vibrations, when you have isotropic vibrations, is to try to classify them. So of course there is an obvious notion of isomorphism of isotropic vibrations. So that just means that they have a symplectomorphism between the two symplectic manifolds that intertwines the projections. And so we would like to know what are isotropic vibrations up to this notion of isomorphism. So that's the classification problem for isotropic vibrations. And basically this problem was solved by Delzin and Azor, but there are some issues about the way they did this. And so I want to tell you how I believe one should look at this classification. And that's where these symplectic gerbes are going to appear. So let's look first very quickly at the Lagrangian case, just to comfort ourselves and remind ourselves a couple of things. So if I have a Lagrangian vibration, the first thing that it determines, it's an integral affine structure on the base of the vibration. And you can think of an integral affine structure. You can think of it as a Lagrangian Z n subbundle of the cotangent bundle, I mean, the most geometric way is to think that you have a special atlas and that the transition functions for this atlas are integral affine transformations of Rn. So every Lagrangian vibration, you have this integral affine structure on the base, and that allows you to define to associate to the vibration a symplectic torus bundle, which is just the quotient of the cotangent bundle by this lattice lambda. It's symplectic because the canonical symplectic form descends to this quotient, since this lattice is locally generated by closed one forms. And this symplectic torus bundle acts on the vibration. So each torus on this bundle acts over the fiber, over the point where the torus is. So if I fix a point in M, I will have, if I fix a point in M, I will have a fiber, which is a torus, and that torus acts on the fiber of X over that point. And that action is transitive and free. So that's the first ingredient. The second ingredient, it's what's called the Lagrangian Chern class of this vibration. And that's basically defining the same way that you define the Chern class of a torus vibration. The only thing is that when you go through the construction, you choose a covering where you have sections which are Lagrangian sections of your vibration. And then you look at the intersection of those things, and you get a check cohomology class, defining a cohomology class in the check cohomology with coefficients in this torus bundle. But because we took Lagrangian sections, you get what's called the Lagrangian Chern class. And then the basic result, very old result, due to Toystermaat, says that two Lagrangian vibrations are isomorphic if and only if they determine the same integral affine structure on the base, and if they have the same Lagrangian Chern class. Oh, I'm sorry. Sorry. Let me disconnect my phone. Sorry about that. So that's the first thing. And the second thing is that there is also a construction procedure. So if you are given an integral affine structure, and if you are given any class in this cohomology, there exists a Lagrangian vibration, unique, of course, up to isomorphism by item 1, that induces this integral affine structure, and it has this class as the Lagrangian Chern class. So this completely solves the problem of classification of Lagrangian shunt classes up to, if you want, the classification of integral affine manifolds. Just as a remark, I mean, this classification giving, if it gives an identification of Lagrangian vibrations with a fixed integral affine structure with this cohomology, it means that there is a group structure, because this is just an abelian group, and so there is a group structure on the space of Lagrangian vibrations with a fixed, inducing a fixed integral affine structure, and that's very easy to see what it is. So if I have two such Lagrangian vibrations, I can define what's sometimes called a fusion product by taking the fiber product and then taking the quotient by the action of the symplectic torus bundle. And this comes naturally with the symplectic form. It's a symplectic form induced by the restriction of this difference of the projections of the forms on x1 and x2. You restrict to the fiber product, and then that descends to the quotient and gives you a symplectic form on the quotient. And that's a new Lagrangian vibration. And this makes the isomorphism classes of Lagrangian vibrations into a group. The unit is the symplectic torus bundle that you have associated with the integral affine structure, and the inverse is just obtained by switching the sign of the symplectic form. Okay, so that's very quickly how you go through the case of Lagrangian vibrations. Now let's go to the isotropic case. So the first remark is that the base of an isotropic vibration has a unique Poisson structure, making the projection a Poisson map. And the reason is very simple, because it's a submersion. You can identify with connected fibers. You can identify smooth functions on the base with functions constant on the fibers, and the ordinary Poisson bracket associated with the symplectic form omega. These functions are closed under this bracket, and therefore you get the Poisson structure on the base. So there is a picture that you can make to view what is an isotropic vibration. So this is the picture. So I have on the top my symplectic manifold X, and if I fix a point M on the base, I have the fiber. And as part of the definition, the symplectic orthogonal to the fibers is an integrable distribution. So there is a foliation that it's tangent to the symplectic orthogonal to the fibers, symplectic orthogonal foliation, if you want to call it that way. And because the fibers are isotropic, these leaves contain the fibers. And the projection of these leaves, because since they are saturated by fibers, they project to a foliation downstairs, and the foliation downstairs is exactly the symplectic foliation associated with the Poisson structure on the base. So that's the picture that you should keep in mind for an isotropic vibration. So that's the first thing you realize, that there is this Poisson structure on the base that should play some role. And the other thing that this picture suggests, and it in fact is true, is that if you take a transverse so a manifold of complementary dimension to the symplectic leaves downstairs and intersecting the leaves transversely, if you restrict your vibration to such a transverse, then what you get is a Lagrangian vibration. So that's this remark. So I fix a transverse to M, to the symplectic foliation, I restrict the vibration, and I get a Lagrangian vibration. Now remember, the base of a Lagrangian vibration had an integral affine structure. So what this is saying really is that transversally to the symplectic foliation, there is an integral affine structure. And so that was realized by Dazor and Delzin, that the base of an isotropic vibration has a transverse integral affine structure to the symplectic foliation. The way to deal with this is to deal with the lattice that now does not, it's still formed by closed one forms, but these are closed one forms that annihilate the directions of the symplectic foliation. So these are a lattice full rank living on the conormal bundle to the foliation. So that's the transverse integral affine structure that now you have on the base. And so what Dazor and Delzan did after they realized this was, well, let's mimic what Duisermar did for Lagrangian vibrations. And they did that, but while doing that, they faced some issues. The first issue is that if you, just like what you do in the Lagrangian case, you try to form a symplectic torus bundle by quotienting by the lattice, well, you get a torus bundle, but it's not symplectic. Well, the reason is clear, because you have to first restrict the canonical symplectic form of the cotangent bundle to the annihilator of the distribution defining the foliation, and now you lose the maximal rank. It's not a non-degenerate, it's degenerate, and so you get a closed form of constant rank now. So this is not a symplectic torus bundle, it's a pre-symplectic torus bundle. Well, that doesn't look too bad. Well, almost, because there is no analog of the Lagrangian Chern class now. And in fact, these isotropic vibrations do not have a group structure. So you cannot hope to have a Lagrangian Chern class or an identification of isomorphism classes of such vibrations with some cohomology group. And so because of this, they do some stuff, and the classification is a bit more weird. Now, what I advocate, and so that's where we start, is that based on some work that I did with Maurice Kreinig and David Martinez Torres on something called Poisson manifolds of compact type, abstracting from that work, we can realize that an isotropic vibration determines a symplectic groupoid. And the symplectic groupoid has some properties. So first of all, the source fibers are connected. It integrates the Poisson structure on the base. And because this Poisson structure has a regular symplectic foliation, this groupoid is regular. And the isotropy bundle, well, actually the connected component of the identity of the isotropy bundle of this groupoid is exactly the torus bundle that we have here that played a fundamental role in the work of Delzan and Dazor. And moreover, if you have isomorphic isotropic vibrations, you get isomorphic symplectic groupoids. So this is kind of like a fundamental, the same way that for a Lagrangian vibration, there is associated an integral affine structure if you prefer a symplectic torus bundle. Here, associated to an isotropic vibration, there is associated this symplectic groupoid. I mean, I have here some words about why this is true. So first of all, Poisson manifolds in general do not have to integrate to a symplectic groupoid, but these ones arising from isotropic vibrations do integrate to symplectic groupoids, and there is a canonical integration. And basically what you have to do is you have to quotient this canonical integration by this lattice defining the transverse integral affine structure. And for that, you have to identify this lattice with a subset of things called cotangent paths. This groupoid is obtained as some kind of Poisson version of the homotopy groupoid in topology. So it's formed by cotangent paths, modulo cotangent homotopy. Inside these, the lattice has, you can associate to the lattice some constant cotangent paths, and so you can identify this lattice inside this groupoid, and then you can take the quotient, and it's still a groupoid, and it's still a symplectic groupoid. So that's basically how this goes. And so, as I was claiming, the Q remark is that when we pass from Lagrangian to general isotropic case, the symplectic groupoid is the correct generalization of the symplectic torus bundle. Is not the torus bundle that Dazor and Dazor considered. That's just part of it. Let me just give you a very concrete example so that this doesn't stay so up in the air. So here is an example of an isotropic vibration. So you start with the cotangent bundle of the two-sphere, and using, say, a Riemannian metric, we can identify the cotangent bundle with the tangent bundle. And so I think of the tangent bundle as pairs of vectors in R3, where the first vector is the base point, has norm 1, so it's in the sphere, and the second vector is tangent to the sphere, so it's orthogonal to the base vector x. And now the map is just a map, it's just a vector product of x and v, of the pair xv. And that's a map into R3. If you look at the fibers of this map, the fibers outside the origin are S1s, are circles. The fiber at the origin is the zero section, so it's S2. And these are isotropic submanifolds. So this map has fibers, isotropic submanifolds, but of course it's a singular fibration because the fiber at the origin is a dimension different from the other fibers. But if you throw away the origin, which amounts to throwing away the zero section of the cotangent bundle, you get an honest isotropic fibration. And this is a very geometric example, and this is the kind of example one is looking at. And in this case, the Poisson structure induced in R3, or in R3 minus the origin, is a linear, is what's called a linear Poisson structure. It's given explicitly by the formulas that I wrote here in the slide. Now, what is the groupoid that you get out of this fibration? Well, the groupoid is very simple. You take the group SO3, you consider the usual action on R3 by rotations, and you form what's called an action groupoid. You throw away the origin because we throw away the origin, so I get a fibration. And so the groupoid is the action groupoid of SO3 on R3 minus the origin. And the torus bundle is the connected component of the identity of this isotropy. It's actually, in this case, it's connected the isotropy. So it's obtained by looking at each point different from the origin and the rotations around the point, the axis, the line through that point. So it's just the isotropy of the action of SO3 on R3 minus the origin. And that gives you this torus bundle. In this case, is an S1. And I don't know what
Quick, can I ask a question?
Of course. Go ahead, please.
So what if you do the same example, but instead of the start of S2, you take R4 minus 0 and the projection on R3 minus 0 by the radially extended op vibration? It looks very similar, except that you don't have this S2 missing. You only have a point.
Yeah, I think it's also an example. Yeah. Yeah, okay. I think it works exactly the same way. Yeah.
But is there a way in these, the groupoid will be different or something like that? I don't know.
No, I mean, I think the groupoid is going to be the same. It's not going to be different.
Okay.
Because the Poisson structure on the base is still going to be this linear Poisson structure.
Oh, okay.
But, yeah.
Okay, thank you.
Yeah, sure. You're welcome. You will see later why I choose this example. As you can see, I mean, there is of course, you say, why do you want to throw away the origin? You should consider the origin here, and then you get a singular fibration. So that's going to be an example of multiplicity-free fibration. All right, so where does these symplectic gerbes appear in the story? So first of all, I'm not going to tell you exactly what is a gerbe, but basically, an S1 gerbe is some kind of higher analog of a principal S1 bundle. And you can replace S1 by a torus bundle, and you can get T gerbes for a torus bundle, and it's some kind of analog of a principal torus bundle. Now, to be very concrete for the talk, I will think of a T gerbe as given by a short exact sequence of groupoids, where the first groupoid is a torus bundle, T. Okay. In fact, most of the times, this groupoid here will be very special. And I'm cheating a little bit because a T-gerbe is really not just a short exact sequence, is what's called a Morita equivalence class of such sequences. And then this, because of that, because it's a Morita equivalence class, this groupoid here is also up to Morita equivalence. So in fact, this groupoid, it's really defining a singular space, a differentiable stack, which is this denoted here by this letter B. And so in general, this short exact sequence, if this groupoid defines the stack B, is really should be thought as a T-gerbe over B, in the same sense that you would consider a principal bundle over B. So that's B is the base of the gerbe here, if you want. Most of the times, this groupoid is, as I was saying, is very special. Is what's called a proper Ital groupoid, and what that means is that the stack that it's representing is very mild. It's an orbifold, maybe ineffective, but it's an orbifold. Now, for us, what is the gerbe that it's appearing? Well, the gerbe that it's appearing is associated with this canonical groupoid that I told you. It's associated with the isotropic fibration. There was a groupoid. And that groupoid had an isotropy given by a torus bundle. And the quotient turns out to be what's called the holonomy groupoid of the foliation, the symplectic foliation of the base. And there is a very close connection between the symplectic geometry of this groupoid, because the symplectic form on the groupoid pulls back under this inclusion to this canonical symplectic form that we have on the torus bundle. And all this happens up to now, not general Morita equivalence, but under symplectic Morita equivalence. And so such a sequence defines what's called a symplectic gerbe. And moreover, the base now is given by the stack associated with this groupoid, but because this had a transverse integral affine structure, and this stack, at least if it is proper Ital, which doesn't have to be, but if it is proper Ital, then what you get is that this stack is an orbifold, but a very special orbifold. It's an integral affine orbifold. So the analog of an integral affine manifold, but now in this singular world of stacks. So there is this very rich geometry associated with this canonical object associated with the isotropic fibration. Now, we all know that principal torus bundles have associated Chern classes. We can consider symplectic principal torus bundles, of which the Lagrangian vibrations that we talked about before are examples, and that have associated Lagrangian classes. And as I said, these gerbes are some higher analog of principal bundles, and so there are also classes associated with these gerbes, and so associated with a T-gerbe, there is what's called a Dixmier-Doisy class, which now lives. So I don't have time to go through this, but the Chern class lives in these Czech cohomology with coefficients in the torus bundle. The Lagrangian Chern class is in the coefficients of in the Lagrangian sections of this torus bundle. Now, the general T-gerbes, the Dixmier-Doisy class, lives in H2 with coefficients in this torus bundle, which can be identified with H3 ordinary cohomology with coefficients in the system of coefficients given by the integral affine structure. Similar to the Chern class, that's what you usually think of the Chern class as a class in H2. But these Lagrangian ones you cannot identify with so simple with the ordinary cohomology in a system of coefficients. Anyway, going to the symplectic gerbes, there is also what's called the Lagrangian Dixmier-Doisy class, which now lives in the version of this cohomology with the Lagrangian sections, or sheaf of Lagrangian sections. Again, this thing also has a group structure, so given two symplectic gerbes, you can multiply them, and you get a new symplectic gerbe. And now the first theorem in this business is that given a regular source-connected symplectic groupoid of the sort that appears before associated with an isotropic vibration, so this one has isotropy, I should really say connected component of the isotropy at torus bundle, there exists an isotropic vibration inducing this symplectic groupoid if and only if the class of the gerbe is trivial. So if this Lagrangian Doisy class is trivial. So this is something new that you don't see in the Lagrangian case. In the Lagrangian case, there was always associated with the integral affine structure. You could always find, once you fix the the class, you could find a Lagrangian vibration. Here, that's not true anymore. So that identifies the kind of symplectic groupoids that you want to see, that you want to look at, is the ones that have trivial gerbe. And then using that, you can move on to the classification of isotropic vibrations. And now the point is that there is not an origin, there is not a canonical isotropic vibration for a symplectic groupoid with trivial gerbe. What you can say is that if you are given two isotropic vibrations that induce the same symplectic groupoid, you can associate to these two isotropic vibrations a class in the cohomology that you would expect. And so there is a relative Lagrangian Chern class now. And the theorem of the classification says that if you look at isotropic vibrations inducing a fixed symplectic groupoid with trivial gerbe, modulo isomorphism, it is in one-to-one correspondence, so it is an affine space modeled on these Lagrangian, on these cohomology that where this relative Lagrangian Chern class lives. So this is not anymore an abelian group, is like an affine space model on this abelian group. And there is a geometric realization of these, and given that I'm already running very much out of time, I think, although I started slightly late, I'm going to jump that. I'm just going to tell you the definition of a multiplicity-free vibration. So you want to study these objects in the singular case, as we know very well in symplectic geometry. If you want to look at Lagrangian vibrations, if you stay within the world of regular Lagrangian vibrations, you want to go that far, you want to look at singular Lagrangian vibrations. Here, the same thing, you want to look at singular isotropic vibrations. But probably looking at arbitrary singular isotropic vibrations is just too wild. And motivated by this, by what we understood now about the regular case, my suggestion of the right definition is that a multiplicity-free vibration is a singular vibration. Now, the base is a Poisson manifold, so that's part of the data, which is integrable by a symplectic groupoid. And this symplectic groupoid acts on the vibration in a way that the symplectic reduced spaces are points. So all this was happening in the regular case, although I did not tell you about item 2 very explicitly. So non-singular isotropic vibrations are multiplicity-free. These conditions guarantee that the regular fibers are isotropic. And one of the main examples of such multiplicity vibrations comes from the theory of multiplicity-free Hamiltonian spaces. Why? Well, the same way that you can think that the first examples that you should look at singular Lagrangian vibrations are the vibrations associated with toric manifolds. So the generalization of toric manifolds to the non-commutative world is multiplicity-free spaces, if you want. And so what that means is that I have a Hamiltonian G-space, and the Hamiltonian G-space is multiplicity-free if the symplectic reduced spaces are points. And this amounts to, in my definition, to think of this moment map as a multiplicity-free vibration. It's the same thing. And so in the case that I was telling you about the two-sphere and SO3 acting on the two-sphere, when you leave the action and you don't throw away the origin, you get a singular vibration, and it's a multiplicity-free vibration. And multiplicity-free spaces, you can classify them. They've been classified by Loja and what's the German guy? I forgot the name now. And so this is the kind of thing that one wants to look now beyond the regular case. And I have a current project with Daniele Sepe, which looks first at the local classification of the singularities, at least the non-degenerate singularities that appear for these multiplicity-free vibrations. And from the global side, we would like to start understanding the global classification of multiplicity free fibrations that have mild singularities. And sorry for running over time. Thank you for your patience. And that's all.